Hey guys, welcome to 9.3a Logarithmic Functions. So we are talking about log functions today, and you may have seen these before. They relate very closely to exponents. The idea is, let's look at this first example. If 2 squared is equal to 4 and 2 cubed is equal to 8, then 2 to what power is 6? As you can imagine, it's got to be a number between 2 and 3, because those are the exponents that get us 4 and 8. So we want to know, how do we find it? And there is a specific way to go about finding it. And we use what are called logs. Logarithms are how many of one number do we multiply to get another number. So how would we solve this idea? 2 to the x equals 8. So you have to think about 2 to what exponent, what power would give you 8. And we can figure it out pretty easily. It would be x equals 3. So the idea, though, is could we write this in a different way? An exponent and a log. They're the same idea, and you just have to correlate the pieces together. So log, here we have log base 2 of 8 is equal to x. So the little number here, that's our base. That's, in this case, that's the base. So those are the same thing. Whatever the base of your exponent is, that's what goes there. 8 is the number that we get out as our outcome, so 2 to some power equals 8. And then over here on the other side of the log, this is your answer. So x is the exponent. Whatever the log equals, that's the exponent. It'll make a little more sense the more we practice this. So here's a diagram just showing how you can rewrite logs and exponents back and forth. So log base b of y is equal to x, or b to the x power is equal to y. And given that b has to be greater than 0, y has to be greater than 0, and b cannot be exactly 0. All right, so we want to rewrite each of these in exponential form. So the first thing that I always do is I identify my base. So 2 is the base. Then we're going to have an exponent, and that's whatever the log equals. So what it's going to be is 2 to the 5th equals, and then our last number here, the 32. And if you think about it, 2 to the 5th power, 2 times 2 is 4, times another 2 is 8, times another 2 is 16, times the 5th 2 gives us 32. So it should work in an equation. This one here, identify the base, and then I like to do this to remind myself that that's the exponent. So the exponent of 9 to the 1st does equal our last number of 9. This one here, that's our base. It's going underneath the exponent, so 10 to the 0 equals 1. This time, and anything to the 0 power does equal 1, so that should make sense. This one you have to be a little careful of, because we have 1/5 as our base, and we're taking that to the -2 power. So 1/5 to the -2 is supposed to equal 25. And if you think about it, well, what happens with a fraction and a negative exponent is it's just the reciprocal, and the reciprocal of 1/5 is 5 over 1, and then that would turn into a positive exponent, and this would end up being 25, 5 squared. So it does work out. All right, now going backwards can be a little bit trickier. So now we want to write these exponentials in the log form, so the logarithmic form. 4 squared equals 16. So start out by thinking about your log. What is the base? Well, the base of our exponent here is 4, so that's going to be the little number. And then a log always equals an exponent, so that's the next part, so it's got to be 2, and then 16 is the piece that's left over. So log base 4 of 16 is equal to 2. Let's try this again. Identify the base, which is 2, so that's the little number. It equals the exponent, so that's 3, and then 8 is the leftover. This one, log base 2 again, equals the exponent, -3. Leftover number goes here, of 1/8. So log base 2 of 1/8 equals -3. We can also evaluate logs, and we're going to need to be able to do a lot of these by hand. So what we do when you don't know what the exponent is you set it equal to x. So we have log base 3 of 81 equals x. So each of these, we don't know what the exponent is, so we're just going to put equals x, and our goal is to solve for x. So we identify the base, And we rewrite it as an exponential function because it's just easier for us to understand when we visualize it like that. So 3 to the x has to equal this number here of 81. Then you just have to think for a second, 3 to what power is going to get you 81? So this one would be x equals 4. You have to kind of remember a lot of your common exponents for these. This one is a little tricky. I'm going to do log base 1/4 of 256 equals x. So our base is 1/4, x is the exponent, and 256. So we're working with a fraction, and you have to think about, well, how am I going to make a fraction a larger number? Think about what we did up here with this problem, with the -2 and the fraction. So the idea is x is going to be a negative number right here. So if we were to think of x to the -1, or not, x equals -1 is what I meant to say. So if we had 1/4 to the -1, that would just be +4. So that's not big enough. So then we got to think, well, 1/4 to the -2. Well, that would be the reciprocal, and then it would be it would be 16. And then we do 1/-3, and that would be 64. Still not big /enough. So we try 1/4 to the -4th. And then you would have 16 times 16, which is that 256. So x would equal -4 on this one. -4. This one, we have a decimal. So identify your base, take it to the exponent, 10 to the x equals 0.001. Now when you have log base 10, that's nice because remember how this works is we can just count the decimal places. Think about scientific notation. 1, 2, 3. So the number's getting smaller, so this would be x equals -3. Because we had to shift our decimal over 3 places to make it bigger. And then we have this one here, log base 64 of 2 equals x. So 64 is our base. We're swinging it underneath to the x. We need that to equal 2. So we need this to be a smaller number. This is where it can also be tricky. Because if we were to do a negative exponent, watch what happens. If I did 64 to the -1, I get 1/64. I don't want a fraction, so I need a number that isn't a negative number, but it's going to make it smaller. And if you think about the last unit, what we had that would make it smaller down to 2 is actually going to be fractional exponents. So we need to think about 64 to some fraction. So let's start with 1/2. So 64 to the 1/2 would be the square root of 64, which is 8. That's not enough, so we got to try a different one. Then we could try 1/3. So that would be the cubed root of 64. Cubed root of 64 would be 8 and 4. 8 breaks up into 2 and 4, and then we would get, oh, I messed up. This should have been an 8 here. 8 and 8, and then we get 2 and 4, 2, 2, 2, 2. So we got a group of 2's here and a group of 2's here. So we end up getting 4. Still not enough because it would be 2 times 2. Then we would have to try 64 to the 1/4 power. Okay, so that'd be the 4th root of 64. It's going to be 8 and 8, and we would do the same thing. For this one, 64 to the 1/4, it's not going to work out to be a 2 on that one because this would give us 4, 2, 4, 2. If you look at the broken down version, we have 6 total 2's. So that would mean we would need the 6th root of 64. So that would be the 1/6 power is what we're looking for on this one. So 64 to the 1/6 would equal 2, so that says x equals 1/6. All right, those are going to be the most challenging ones. The next one, we have some special logarithm values. Let b be a positive real number such that b cannot equal 0. The logarithm of 1 as a logarithm of base b. So log base b of 1 equals 0 because b to the 0 power equals 1. And log base b of b equals 1 because b to the first power equals b. We also have some more vocabulary. A common log is a logarithm with base 10. Your calculator is set in this common log mode. Your natural log is this logarithm with base e, and that looks like this. It's the natural log, and it's ln. You can use calculators to use common and natural logs. So if you don't see the base of a regular log like this, the base is 10, and if you don't see the base for a natural log, the base is e. So let's go ahead and evaluate this. So log base 64, or log base 4 of 64 equals x. 4 to the x power would equal 64. This one, if you just remember, x would have to be 3. 4 to the third power would give us 64. This one we would set equal to x. So this one we did earlier, I believe. Yes, so we can skip over this one. This is a good one. This would equal x, so base 2, 2 to the x, and then would equal 1/8. So it's making it a fraction, and we're trying to go from 2 to 8. So this is going to be a negative number. It's going to be x equals -3, because 2 to the third power would give us 8. And then this one, we have 32. So we're trying to get to x, 32 to the x equals 2. It's making it smaller, but it's not making it a fraction. So we need to think about x. This is another one of those examples where x is going to be a fraction. So we need to get 32 down to 2. So what you can do is just factorize this, prime factorization, 8 and 4, 2 and 4, 2, 2, 2, 2. So count the number of 2's, and there's 5 of them, so this would be x to the 1/5 power, or x equals 1/5, excuse me, since it's going to be a fraction. All right, and now these ones you're going to need your calculator. So log of 7, because we don't see the number, so how you type it in, find the log button. So here's log, and it gives us base 10, and then of 7 would be 0.8, we'll just do 2 decimal places, so 0.85. So this would equal 0.85. And then I'll do the natural log of 0.25. So that is this ln of 0.25, and it gives us negative 1.39 is what we'll round that to. And that is it for logs. So we're going to practice a lot more of these. I know it might be confusing the first time through, but just remember that logs can always be rewritten as exponential functions and so forth, and that's what's going to help.